All right, here we go with the third type of stress that we can impose on a Le Chatelier equilibrium system. The third one is making changes in pressures and volumes of the gas components. Now this kind of throws us back towards gas laws, and it's one of our few connections back to that particular unit. There are three ways in which we can change the pressure and therefore the corresponding volume of a gas equilibrium system. Easiest ways would be to add or remove a gas as reactant or product. Now that's super easy. That's actually just like what we were doing in part one where we were changing concentration. We can add an inert gas, which is something that wouldn't be involved in the reactions, but might change the relative pressure that we have in that vessel because you have more collisions with the surfaces, and therefore this would cause relative changes throughout. And the most common one would be to change the volume and therefore the pressure of the container. This one's a little bit tougher to figure out because we have to make connections back to the number of moles. Now, if we were in class, I would geek out and take you guys all the way back through some of our discussions in gas laws and get us thinking about Avogadro's law again, volumes being directly proportional to moles. We could take a look at the ideal gas law, which you see at the bottom of the page, and try and make references there. That's an awfully long and involved discussion, and I do it in some semesters, I don't do it in others. It all depends upon the interests of the class. Being that we're doing at-home learning and the complexities of making this connection, what I would suggest you guys do is just memorize the relationship. If I decrease the volume of a vessel, I will shift equilibrium to the side that has the fewest number of moles in that particular problem. If I increase the volume, therefore decreasing the pressure, I will shift to the side with the greatest number of moles. Because you guys will be researching this and have this stuff available to you when questions do come up on the quiz, if you get something that involves changes in pressures and volumes, you can research this and answer the question. We can save the big discussions as for the why, maybe for another course. We could also, if you like, it just kind of dawns on me right now, that we could make a connection back to the concentration one of our first examples. If I was to decrease the volume of a system, then it would also increase the concentration of any gas in that system. Think about it. I'm changing the volume in liters. If I make that smaller, then my mole per liter number goes up because the gas still can't change. So we could start talking about what would happen with respect to concentrations as well. So let's look at that as the example. Maybe we'll talk about concentration as a way that you can look at these problems. Here's a calcium carbonate decomposition sitting in equilibrium. You have solid calcium carbonate, you have calcium oxide, and you have carbon dioxide. You only have one gas in the system. You notice that there is a stress, that the volume has been decreased. All right, I've pushed the piston plunger in, and I've decreased the volume of this particular vessel. I've also increased the pressure. The system has to shift in a direction in such a way that more carbon dioxide is going to be consumed. Let's look at this from a concentration point of view. If I decrease the volume of this vessel, then I also increase the concentration of carbon dioxide. Now, if my stress is ultimately to increase the concentration of carbon dioxide, which way do I need to shift in order to deal with this imposed stress? Do I shift right and produce more calcium oxide and more carbon dioxide, or do I shift left to cause a decrease in carbon dioxide and the amount of calcium oxide? Which one makes sense to oppose this stress of decreased volume, increased pressure, and the increased carbon dioxide concentration? Hopefully we see that it's a shift left. That would cause a decrease in the relative concentration, and we would get increased amounts in the other two. All right, if we take a look at the number of moles, I have 2 moles on this side, I have 1 mole on this side. Go back to what we set up here. If I decrease the volume, which I did, I always shift to the side with the least number of moles of gas, which I did. All right, so there we go. That's the 3 different situations that we have dealing with Le Chatelier's principle the stress, that is imposed, and the response to that stress to oppose that particular imbalance that we put into the equilibrium. We can look at another one here. This is something that we would do in lab with you guys. Consider that you have dinitrogen tetroxide, imbalance, with 2 moles of nitrogen dioxide. Nitrogen tetroxide, all right, is clear and colorless. And nitrogen dioxide is a brownish, reddish kind of gas. We've shown that the images of the syringe here are showing this. Now, unfortunately, this is in black and white. All right, but you can see some relative changes. Take a look at what's going on. If I decrease that volume to this point here, I would have increased the concentration of both gases. I would not notice any visible changes with the clear colorless one, but if I increase the concentration of nitrogen dioxide, my brownish red color should intensify. And you can kind of see with the relative contrast here that it has. So, how does this system oppose this action? All right, well, I've increased the concentration of 2 moles of nitrogen dioxide. I've increased the concentration of 1 mole of dinitrogen tetroxide. Which way should I shift? Well, we said through the memorized approach that it will always shift to the side with fewer moles. 1 mole here, 2 moles here. So if I shift left, I consume more of my reddish-brown nitrogen dioxide. Take a look at the picture. What do you notice? Is the color as intense after the stress? Or has it diminished a bit? It has diminished, and so we see evidence that the shift was indeed to the left. Just like concentration, because it is just a concentration problem, initial and final K values are the same. I would take a look at this video because it does show this exact same thing here in color and in real time. Okay, so please take a look at that video if you're having a hard time with this. Last thing that we should talk about here before we get into the video or the examples in the next video is catalysts and your equilibrium system. Remember that a catalyst was a substance that just lowered the activation energy curve between reactants and products, but it would do it the same way or the same amount to both sides. All right, so it's going to increase the reaction rate to both forward and reverse because it lowers the activation energy for both reactions equally. Therefore, the catalyst will have no effect on these systems, and it will not cause any sort, or we will not see any sort of Le Chatelier shift. This was a great way that, again, the diploma exam would test to see if you were paying attention. Catalysts, we know, speed the rate of reaction, but it does so equally for both reactions. All right, in our next video, we're going to get into the examples. We'll go through a few, but not all, and we'll see how that goes.